Hello and welcome to day 12. The focus of day 12 is case analysis, um, the process of looking at something and seeing what your possibilities are. But it's actually quite a bit of a grab bag. We're going to learn another big set of new tactics. So it is another long day full of videos. I think tomorrow, the next day, day 13, will also be a long day. And then after that, I think we'll be able to maybe start to dial things back a little. But we can look forward to sort of picking up all of this new stuff over the next few days. So let's get started. We're going to learn a new tactic, and it's going to be a really great hammer. We're going to pound a lot of nails with it. Um, destruct. It's for case analysis. So to motivate it, I want to show you something that you hopefully believe is true, but the tools we have so far don't let us prove. Okay, let's get started. So you'll see will be common throughout the textbook, theorems that aren't going to work get names like first try, take one. And that's kind of a clue that it's not going to work. Now, I wish it worked this way in the real world, that you know to name something take one when it might not work. And in fact, mathematicians out of superstition will often write conjecture on the board rather than theorem until they're really done, and then you erase conjecture and theorem to celebrate. In any case, let's look at this thing that ought to be a theorem that we don't know how to do yet. For any natural number n plus 1 is not judged equal to 0 by the function EQB that checks whether or not two natural numbers are. EQB on n plus 1 and 0 should return false, because we believe they're not really equal. Okay, this I think makes sense for the naturals, right? If you're thinking of the negatives, like the integers or whatever, okay, we'll choose -1 and there is such a number. But for the naturals, there really is no number you can add 1 to and have it be equal to 0. So you might bravely dive in and say, okay, cool, let some n be given. I need to show that EQB n plus 1, 0 is equal. Okay, well, Cock, could you run this program for me? Maybe you'll figure something out. And it does nothing. So why does it do nothing? Well, let's recall the way that plus was defined. Plus is defined to be recursive on its first argument. So you might look at this and say, oh, but look, I know, but there's just a 1 there, so it's really just going to add one successor to n. And I agree with you that that's really just what it's going to do. But the way plus works, it'll actually add n successors to 1. So Coq doesn't know what n is, so it can't run the program. Right? It's no good. So we'll run the abort command, which is a little bit different from admitted. Admitted leaves the name around, but it's marked as sort of an incomplete proof. Abort pretends like it never happened. So you should be using admitted. We'll use abort occasionally in a script to not clutter the namespace with sort of um, the detritus of broken proofs. Okay, so how do we do this? Well, though, the argument that I would make for why this proof ought to go through is, well, look, it doesn't matter what n is. N could be one of two things. If n is 0, then the sum here will turn into 0 plus 1 is 1, not equal to 0. EQB can figure that out. We're good to go. If n is successor of something, then this thing, okay, this will be s of n prime plus 1, let's say. And that, when I run the plus, that'll be s of n prime plus 1 quantity. And then we'll have a successor here and a 0 here, and the way we've defined EQB will mean that that'll return false then. Right? So either way, it should be the case that this returns false, and we can see it just by unfolding one level of n, saying like, look, n could be one of two things. Which is it? I'll show you that in either case my proof holds. Okay, we can formalize that reasoning in a tactic called destruct. Destruct you can think of as meaning, hey, let's break this thing apart. I want to see what the possible ways it was constructed are, right? Like taking apart a clock or a toy or something. So, okay, destruct n. And now here we're going to say, well, what names would we like to give for the subparts? And so this little bracket is what's called an as pattern. It comes after this keyword as. This is doing nothing. It's just saying, I'd like to destruct n as, and then we give the names. And the general syntax here is that you'll have square brackets, and then you'll have a pipe between each alternative. And if there's any argument to those alternatives, the way that S takes a single argument, you'll name the subparts, right? So for now, I think it's really common. Like, we'll understand by the end of the day, maybe by the end of 1 or 2 days from now, you'll be very skilled with these. But for now, I think you can look at them and say, okay, this is just the thing to write for a natural number, right? If this is m, it'd be bracket pipe space m prime to talk about, look, either it's 0, that's the nothing named there because 0 has no parts, or it's successor of something. You'll notice I don't have to write the s or anything. The cases here are kind of implicit. I'm just sort of outlining what they could be. And lastly, we say EQNE. We'll see what that is in a second. This is asking destruct to remember an equation of about n for future reference. So let's do it. Let's see what happens. Here's our one goal. We suddenly have two goals. Proofs are like hydras, right? You knock one thing off, you're going to have to do something else. All right, so we've got two goals. If you look at the goals we see here, you can see, okay, one, n got substituted for 0. And in fact, we can see in our context the equation e saying that n equals 0. And then in the other, n got substituted for some s of n prime, and we don't get to see the context because we're not at that goal yet. Let's keep trucking. So we'll use a bullet point to say, okay, I'm focused on this one goal. Take a look. Okay, so in this setting, what do we need to do? Well, we need to show that 0 plus 1, 0, given to EQB yields false. If we run simple, we see that it works, right? If you didn't trust it, maybe it's helpful to remember what EQB is. A little smaller so you can actually see it. There we go. But just narrowly missing me. Whew. Took an EQB to the head. So if you look at that, you can see that, okay, look, we're going to be in this case for n and then this case for m, right? Because this is going to be s of something. Okay, great. No big deal. Now let's look at this case. Okay, the goal is the thing we saw before, n has been replaced with s of n prime. But now our equation remembers, hey, that n that you heard about earlier, that's equal to s of n prime. And then conveniently, Cock is sort of remembering for us, like, oh yeah, now you have two nats you know about. You know about n, but you also know about this n prime. I really like this convention. I think when we've been writing programs, I've been a little lax about saying, like, oh, are you going to call the subpart of n, or n prime, or something else, like smaller n or whatever. As we get into proofs, having the prime versions be the various smaller bits is, I think, actually a really great thing to sort of just keep track of who's doing what where, right? As we start breaking up structures as part of our proofs, it's going to be really important. Okay, so in this setting, we know that n is equal to s of n prime, and we need to prove this. It turns out we're not going to need to use e. I just think it's good to get in the habit of always typing eqn. You can leave it off if you don't need it. That's totally fine, right? If we do the proof without it, it just won't generate the equation. You don't need to print eqb anymore. Sorry, thank you. It won't generate the equation, and that's fine. You don't need it. You'll notice also we no longer know about n anymore. N is gone. So in a sense, this is nicer, right? Like we don't have to our cluttered context, right, with variables we don't need. But eventually you might need n again. And then you'll look at this and be like, well, what happened to my n? So if you always type EQNE, you'll never miss it. Okay. So in this setting, again, you can see from the script that it's not going to be so bad. When we simplify this, well, what case are we going to be in? Let's see how this really works. Well, this s of n prime plus 1, that's really going to turn into, right, we'll get something like this. S of n prime plus 1 is going to reduce to s of n prime plus 1. That's how it's defined. But once we have that, then we'll be in that same EQB case where we have a successor in the first argument, but not in the second. All right, in any case, it works. Fantastic. Okay, so there's an informal proof that goes through the motions here. I'm just going to briefly comment on it. Here it's been annotated with the various tactics. So this is something that we'll need to do certainly when we transition to informal proofs, is we'll sort of be doing this sort of, okay, here's the proof in Coq, let's translate it to English. Though by the end of the course, I'm hopeful that you'll be writing proofs in English natively. So the language for destruct in English could be something like we go by cases on n, by case analysis on n. The natural number n could have been constructed in one of two ways. We examine both. All of those are great ways to talk about it. And then you can see here that we have slightly different conventions for when we identify new names. So like here, you could say next, for some n prime or something, right? You could say something like that. There's a lot of different ways to go. This is just some sample wording, but this is the style of informal reasoning that corresponds to destruct. Okay, let's just look at some more examples of destruct. We'll get to see other ways it gets used. Great tactic. Okay, so here, okay, we're going to show, this is, I think, actually our first really truly interesting theorem. This is actually kind of neat. So this is showing that for any Boolean b, neg b is involutive. Involutive, it comes from the involere to damn, one of those where it means to turn inside out. And the idea is like, well, turning something inside out is an involutive operation. If you turn something inside out twice, it's right side out again. I love the imagery of that. So negation turns a boolean inside out, right? False is on the inside of true, and you turn it back inside out again, you get a true again. Okay, great. So what this means is neg b of b is just equal to b. So how will we prove it? Well, let b be given by cases on b. Now you'll notice here I don't have an as pattern, right? The reason I don't have an as pattern is because there's no interesting subparts. There's no need for me to name any of these because, look, a boolean is either true or false. I could write this because there's no parts to name, but like that's just more typing for not a lot of gain, right? So here again, it's a pipe because, okay, there's two cases. In each of the two cases, the first being true, the second being false, there's no subparts of any interest. So we get here. So in this setting, I would just really write this, right? Okay, so now we have something concrete. Now that we have something concrete for each of our two sub goals, one for true, one for false, we're doing the true goal first. You'll see that Coq will always do this in the same order. It's done in the order that the inductive definitions came, right? So because we defined true before the true constructor before we defined the false constructor, it will always come first in Coq's case analyses. Keeping a consistent ordering is, I think, a really good idea, even in your informal work, just to sort of set reader expectations of like what case is going to come next when. All right, but now that we have something concrete, we again have this equation E hanging around just out of like, safety first. Maybe we'll need to talk about B again. You never know. But here, when we look at it, we just say, okay, neg B, true. This is code that Coq can run. So we can just say, look, I know Coq got this right. Just run it. It's fine. We're totally good. Okay, in the next case, we look at neg B, false. Right, if we run simple, Coq runs it all the way. We're good to go. Okay, so we've done case analysis on numbers. We've done case analysis on booleans. Let's do it on on DNA bases. Okay, so here's the complement function, just to keep it in your memory. So complement, like negation, is also involutive. Okay, let a base B be given. Let me go by cases. Oh, there's 4 cases. One where B is equal to C, one where it's going to be equal to G, one where it's equal to A, one where it's equal to T. Now, if we wanted to, we could have written oh, that. Now, I just got an error message that I get all the time because I forget Coq cares about this. If you have 2 pipes in a row, you need spaces. Now, this is to me again kind of weird. Like, okay, there's 4 blanks. What is it? What was it? C, G, A, T. Fine. I don't think we win anything by writing these blanks, which is why I didn't do it. I believe Coq will also allow us to just do that. To be like, yeah, blow it up for me. Right? Again, I don't see the point in writing this. If you don't want to name any parts of it, don't write a pattern. Okay, but now we have 4 cases. So, okay, interesting. We have to prove this for each of the 4 cases. Now, in each of these cases, this is just something Coq can run, right? Complement of C should give us G, and then complement of G should get us back to C again. Coq agrees. I'll run a simple this time. Yep, it worked. Beautiful. Okay, cool. Another involutive operation. Okay, let's do some fancier proofs. Case analysis to me really marks the beginning of it being able to ask interesting questions and get sort of like theorems that have some value, right? Before now, we were just running programs a little, doing some rewriting with assumptions, but now we're starting to prove things that are, I think, non-trivial, right? The proofs, I think, are not so crazy. I think the hard part here is learning the new syntax, learning the way Coq interacts here, keeping track of all the state in your mind, right? Pointing out to a human that DNA complement is involutive is, I think, not so hard. But even so, I think it's pretty cool that the computer is checking our work, right? I think that's pretty neat. All right, here's another one. This time showing off some nested bullets. I think this is our first properly nested proof. So we want to prove that and B, right, conjunction on Booleans is commutative. Okay, great. So if I take and B of B and C, it'll be the same of and B and C and B. And now Coq is helpfully rendering this as the ampersand ampersand, though it's maybe nice to write it this way to remind ourselves of how this function's defined. Okay, So here we go. Let's go by. I remember that and is written and on its first argument, right? That's the first thing it matches. Though, like, look, with commutativity, whatever is the first argument on one side isn't the first argument on the other side. So you win some, you lose some. Let's do B first. So destruct B, we'll get two cases. Okay. Now, well, what's the answer here going to be? Well, it kind of depends on C, doesn't it? Okay, so let's see what C has to say for itself. Go by cases on C. So you might, if you tried then to do a dash here, Cock will say, wrong bullet. You're not done with the dash level. So I go in the order dash plus star. We could do star. That's fine. But I like the pluses first. Okay, so now we're in the case where B is true and where C is true. And now Cock has sort of kept track for us, right? As we did the destruct, it substituted for B and C everywhere, though the equation clause sort of kept this bit hanging around. So at this point now we see like, well, this is what we have to prove. I feel good about this. This feels very promising. So I'm just going to say reflexivity and we're good to go. Okay, here. In the next case, now B is true and C is false. Okay, I still feel pretty good about this. If I remember how A and B is defined, I feel pretty confident, so we'll go with it. Okay, and now we're done with the first case where B was true. And now Cock is helpfully telling us, focus your next goal with bullet dash. So let's do it. Okay, now we're in the world where B is false. And again, we kind of have to see what C's status is. We'll look at what C does. So, okay, break it up. Okay, B is false, C is true. Compute, they're equal. False and false is equal to false and false. Feeling great. Okay, great. Let's do it differently. Maybe you don't. Maybe you don't want to use bullets. Maybe you're a you're on Team Curly Brace. That's fine. Here's a version of it that does the same thing. Okay. Boop-a-doop. And then it all goes the same. I mean, this feels like way more typing to me, but if you like the look of this or it helps you keep track of things, more power to you. I'm happy for you. Okay, so one last thing that's sort of worth showing. If you're just going to intro something to immediately destruct it, then you can write the as pattern you were going to use instead of the variable name, and it'll just break it up for you right away. Okay, so let's see this for the original motivating theorem that we had. For all natural numbers n, adding 1 to n is not equal to 0, according to our function. Okay, when we say intros with this pattern, this says intros some number, and then by case analysis on it, it could either be 0 or not. Give me those two cases right away. I want my whole proof to be conditioned on this. So this is the same as intros and destruct n as that. Right? It's just exactly that. Now, there's no way that I know of to do the equation here, so maybe not good in those situations where you end up meeting the equation. We haven't been in any of those situations yet. It'll be some time. Okay, this to me is a huge convenience, right? I do this all the time, right? And so the proof goes through just the same. It's just the same as doing those tactics. So there's some practice for you to do it here. Play around with it there. Relatedly, I already showed that if you didn't want to name anything, you can just write bracket. One particularly nice convenience, right? Maybe you looked up here and you were like, why do I have to destruct C twice, right? I said to do it once already. And it turns out there's like really fancy tactics we're not going to talk about that let you sort of like do fancy stuff like, oh, do this for every sub goal or whatever. We're not going to do any of that. I want to keep it very simple. There's already a lot to learn here. But if you use multiple pattern in an intros, it lets you do all your destructs at once. So this way, for this and B commutative proof, by writing this, I destruct B and I destruct C simultaneously. So I'm just going to get all four cases at the top. There's less nesting. I find this often to be a lot nicer. Now, if it were the case that when like B was true, you didn't have to look at C at all, then you'd lose here, right? You'd have more work to do than you would have otherwise. You might have been able to skip some extra destruction. But for this, I think this is a much nicer way to do it. This sort of like, we'll break it all up just right here. So let's see what that looks like. We start the proof. Okay, let B and C booleans be given by cases on B and C. And we just get all 4 subgoals right out the gate. Love it. So each of these is very simple. Right? It's the exact same cases we got in the exact same order. It's just fewer tactics, a little easier to write. Okay, so in the continuation, I'll talk more about uses of destruct. In particular, we'll use destruct to reason with some of the logical connectives that we've seen. Okay, talk to you soon.